Black holes, the most mysterious objects in the universe. They warp time, devour stars, and stretch reality itself. But what happens at their very core? What lurks inside the singularity, where all known laws of physics break down? Today, we're diving into the depths of gravity's ultimate abyss to explore what science and theory can tell us about the center of a black hole. Get ready, because this is where physics meets the unknown. Before we can grasp what happens at the center of a black hole, we need to define what a singularity actually is. In physics, a singularity is a point where a mathematical function, such as gravity or density, becomes infinite. In the case of a black hole, this means that matter collapses to an infinitely small and infinitely dense point. At this level, classical physics ceases to function. The singularity marks the breakdown of everything we understand about reality. Singularities don't just appear out of nowhere. They are formed through the catastrophic collapse of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, the outward pressure that once counteracted gravity disappears. Gravity wins, pulling everything inward until the core is crushed under its own weight. If the mass is great enough, even atomic structure collapses, creating an event horizon, the point of no return beyond which not even light can escape. And at the very center of this dark abyss lies the singularity. Imagine an astronaut falling toward a black hole. At first, things seem normal, but as they get closer, something strange happens. Time itself slows down relative to an outside observer. This is time dilation, a key prediction of Einstein's general relativity. From the astronaut's perspective, they continue falling, but to an outside observer, they appear to freeze at the event horizon, never actually crossing it. But from the astronaut's point of view, they would continue falling, seeing the universe accelerate into a distant future as they approach the singularity. As our astronaut moves past the event horizon, the black hole's gravity begins stretching their body apart. This process is called spaghettification. The reason? The gravitational pull is stronger at their feet than at their head, pulling them into a thin, elongated strand of atoms. No matter what enters a black hole, whether it's a star, a spaceship, or even light itself, this extreme tidal stretching is inevitable. The deeper they fall, the greater the distortion until they reach the singularity, where physics itself stops making sense. Here's the problem. Singularities, as described by general relativity, involve infinite density and zero volume. But infinities rarely exist in nature. They signal that our equations are incomplete. This is where quantum mechanics comes in. While Einstein's equations predict singularities, quantum physics suggests that at extremely small scales, space and time may not be smooth, but instead behave chaotically, forming something known as quantum foam. This could mean that singularities aren't actually infinitely small points, but something stranger, something we don't yet understand. One of the greatest paradoxes about singularities is whether information is lost forever. In 1974, physicist Stephen Hawking proposed that black holes aren't completely black. Due to quantum fluctuations at the event horizon, they slowly leak energy in the form of Hawking radiation. Over immense timescales, this means black holes could eventually evaporate entirely. But what happens to the singularity when this occurs? Does it vanish? Or does it reveal something new about the structure of space and time? This brings us to one of the biggest unresolved questions in physics, the black hole information paradox. If a singularity truly destroys all information, this would violate quantum mechanics, which states that information cannot be lost. Some theories propose that information is encoded in the Hawking radiation itself. Others suggest that black holes may not actually lead to singularities, but instead to new universes, wormholes, or even white holes that expel matter elsewhere in space-time. Until we have a quantum theory of gravity, we may never fully understand what happens to information inside a black hole. Could black holes lead to new universes? Some theories suggest that the singularity may not be an endpoint, but a bridge. In certain interpretations of general relativity, singularities could be linked to white holes, regions that spew out matter instead of sucking it in. This concept, known as a wormhole, has fascinated physicists and science fiction fans alike. But until we can peer inside a black hole, these ideas remain in the realm of speculation. The singularity remains one of the greatest mysteries in all of physics. Black holes push the boundaries of our understanding of physics. Their singularities challenge our current theories, revealing the need for a deeper, unified understanding of gravity and quantum mechanics. But for now, the singularity remains a place where science meets the unknown. What do you think happens at the center of a black hole? Let us know in the comments, and don't forget to like and subscribe for more deep dives into the universe.